Chapter 6, Design a Key Value Store. A key value store, also referred to as a key value database, is a non-relational database. Each unique identifier is stored as a key with its associated value. This data pairing is known as key value pair. Each unique identifier is stored as a key with its associated value. Key value store is also known as a key value database. Design a key value store. A key value store is also known as a key value store or a key value database. The database with the contents stored as a key with its associated value. Each unique identifier is stored as a key with its associated value. This data pairing is known as key value pair. In a key value pair, the key must be unique, and the value associated with the key can be accessed through the key. Keys can be plain text or hashed values. For performance reasons, short key works better. What do keys look like? Here are a few examples. Plain text key can be like last underscore logged underscore in underscore at, and a hashed key can be anything with the combination of numbers and alphabets. 253 double D EC4. The value in a key value pair can be strings, lists, objects, etc. The value is usually treated as an opaque object in key value stores, such as Amazon Dynamo, Memcached, Redis, etc. The value is usually treated as an opaque object. So this is a data snippet of a key value store. So basically, in a key value store, we have some keys with the associated values, and all the keys have to be unique. उनकी keys होंगी सब unique होंगी और उनकी associated value can be similar और जो associated value है that will be an opaque object and it can be strings or text, objects, lists, anything. And keys can be string or they can be hashed values. Now these hash values can be obtained by any hashing function. For example, fmod and hash string holds of that. So in this chapter, we are asked to design a key value store that supports the following operation. Put key comma value, insert a value associated with key, get the value associated with key. So basically दो operations हमें करने हैं इसमें put key comma value जो कि हमारे key value set में एक key डाल देगा with the value and get key which will give the value that corresponds to the key. Understand the problem and establish design scope. There is no perfect design. Each design achieves a specific balance regarding the trade-offs of read, write, and memory usage. Another trade-off has to be made was between consistency and availability. In this chapter, designing a key value store that comprises of the following characteristics. The size of a key value pair is small, less than 10 KB. Ability to store big data. High availability. The system responds quickly even during failures. High scalability. The system can be scaled to support large data. Automatic scaling. The addition deletion of servers should be automatic based on traffic to enable consistency and low latency. So there is no perfect design. Storage trade-offs only. In this case, the trade-offs can be between read, write, and memory usage, and they can also be between consistency and availability. So हमें इसमें क्या करना है? The basic necessary things that we require are high availability. The system should be able to give the results very fast even during failures. High scalability, the system can be scaled when big data has to be inserted. Large data set basically को support करने के लिए and ability to store big data obviously. उसके पास ability scalability करनी है तो obviously it has to have the availability to store big data. and the size of key value pair has to be small. Key value pair का size almost 10 KB तक हो सकता है, like max. And automatic scaling, the addition and deletion of the servers should be automatic based on traffic to enable consistency and low latency. Single server key value store. Developing a key value store that resides in a single server is easy. An intuitive approach, an intuitive approach is to store key value pairs in a hash table, which keeps everything in memory. Even though memory access is fast, fitting everything in memory may be impossible due to the space constraint. No optimization can be done to fit more data in a single server. Data compression, store only frequency used data in memory and rest on the disk. Frequently used data on memory and rest on the disk. Even with these optimizations, a server can reach its capacity very quickly. A distributed key value store is required to support big data. So पहले अगर हम कंसिडर करें a single key value store, basically एक ही server पे सब कुछ store कर दिया. So we can use a hash table which stores everything in a hash table, and all the data is stored in the memory. Directly memory में हम values को key value pairs को hash कर देंगे. But this has disadvantages कि when there is so much data, the memory required will be too much. तो इसका एक वर्क अराउंड है कि हम frequently यूज डेटा को मेमोरी में स्टोर करेंगे और जो डेटा नहीं होता frequently यूज उसको डिस्क में स्टोर कर लेंगे. एंड देयर इज ऑल्सो वन मोर टेक्निक, डेटा कंप्रेशन. बट इनके अलावा भी सिंगल सर्वर पर स्टोर करना इज वेरी हार्ड. So we generally follow a distributed key value pair. So, so distributed key value pair store. We follow this. तो इसमें होता क्या है? A distributed key value store is also called a distributed hash table, which distributes key value pairs across many servers. When assigning a distributed system, it is important to understand CAP. CAP is basically consistency, availability, and partition tolerance theorem. So distributed key value store stores the data in a hash table across many different servers. When designing a distributed system, हमें एक चीज का ध्यान रखना है, which is CAP, consistency, availability, and partition. So CAP theorem says that it is impossible for a distributed system to simultaneously provide more than two of these guarantees, which are consistency, availability, and partition tolerance. CAP theorem, so distributed key value store में we store the key values in a hash table which is distributed across the servers, and this follows CAP theorem. CAP theorem basically says that for a distributed server, for a distributed system, it is impossible for us to achieve more than two of the criteria in CAP. At max हम टू क्राइटेरियाज को अचीव कर सकते हैं, एंड वो क्राइटेरियाज हो सकते हैं CA, or they can be CP, or they can be AP, or they can be CA, CP, AP, or yes. Hmm. So basically हम उनमें से किसी भी दो को we can be sure we can make them available, but तीन कभी नहीं हो पाएंगे at max तो. So we can either have consistency and availability, we can have consistency and partition tolerance, or we can have availability and partition tolerance. Consistency means that all the clients see the same data at the same time, no matter which node they connect to. Availability means any client which requires data gets a response even if some nodes are down. Partition tolerance. Partition indicates a communication break between two nodes. Partition tolerance means that the system continues to operate despite network partition. Consistency is basically all the users are able to see the same data when they connect to the server at the same time. Availability means that even if some nodes are down, the data is still available to the user. And partition tolerance is basically, partition is defined as the, like, when two servers can communicate, that is known as a partition, a breach of communication. And partition tolerance is basically Even if there is a breach of communication या communication break between two nodes, and the system continues to operate despite the network partitions. Gap theorem states that one of the three properties must be sacrificed to support two of the three properties. So consistency, availability, and partition tolerance, we can have CS, CP, or AP. Nowadays, key value stores are classified based on two characteristics they support: CP, consistency, and partition tolerance. The CP key value store supports consistency and partition tolerance while sacrificing availability. AP, availability and partition tolerance. AP key value, a distributed AP key value store supports availability and partition tolerance while sacrificing consistency. CA, consistency and availability system. Consistency, availability key value store supports consistency and its availability while sacrificing partition tolerance. Since network failure is unavoidable, a distributed system must tolerate network partition. The CA system cannot exist in real-world application. Okay, what you read above is mostly the definition part. To make it easier to understand, let us take a look at some concrete examples. In a distributed system, data is usually replicated multiple times. Assume data is replicated on three replica nodes N1, N2 and N3. तो बेसिकली इसमें क्या कहा गया है कि हम CA, CP and AP को अचीव करना चाहते हैं, बट रियल वर्ल्ड में if there is a break of communication between the servers, that is not like ये नहीं हो सकता real world में, because if there is no communication, then even the user cannot connect to the server. So CA does not exist in real world, but we use RCP and AP. We can have consistency and partition tolerance and availability and partition tolerance. So for an example, assume all the data is replicated on three nodes N1, N2 and N3. इन तीनों nodes में हमने data को replicate कर दिया है. Ideal situation है in ideal world, network partition never occurs. Data returned to N1 is automatically replicated to N2 and N3. Both consistency and availability are achieved. Real world distributed system. In a distributed system, partitions cannot be avoided. And when partitions occur, we choose between consistency and availability. In figure 6.3, N3 goes down and cannot communicate with N2 and N1. If client side data to N1 or N2, data cannot be propagated to N3. If data is written to N3 but not propagated to N1 and N2 yet, N1 and N2 would have stale data. If we choose consistency over availability CP system, we must block all write operations to N1 and N2 to avoid data inconsistency among the three servers, which makes the system unavailable. Bank systems usually have extremely high consistency requirements. For example, it is crucial for a bank system to display the most up-to-date balance info. When inconsistency occurs due to network partition, the bank system returns an error before the inconsistency is resolved. However, if we choose availability over consistency AP system, then the system keeps accepting reads, even though it might return stale data. For writes, N1 and N2 keep accepting writes, and data will be synced to N3 when the network partition is resolved. Choosing the right gap guarantees that fits your use case in an important step in building a distributed key-value pair. You can discuss this with your interviewer and design a system accordingly. So basically क्या है? So let's just say we have three nodes N1, N2 and N3, and um, these are all consistent, and there is no network partition, and all the data is replicated among all the three nodes. So होगा क्या? If there are any write operations on N2, let's say, so those will be propagated to N1 and N3, right? If there is no network partition. But obviously, real world में network partition will obviously exist. There will be a partition. So let's just say that N3 node में कुछ issue है and we cannot communicate with N3. So what happens here is that we have two choices. Either we can conserve CP or we can conserve AP. If we want to conserve consistency and partition tolerance, then what we'll do is we'll stop all the write operations. इससे होगा क्या कि if the user is not able to write, then the data will not become stale and it will stay the same. So when a user reads data and क्योंकि कोई भी write operation नहीं हो रहा था, so the data they read will be consistent amongst all the users. जितने भी यूजर हैं जो भी डेटा रीड करेंगे वो उनके लिए सेम ही होगा. If we block all the write operations, then consistency and partition tolerance will be preserved and we will have a CP distributed key value store. But if you want to have high availability, the data available हो, then we can allow write operations as well as read operations. So होगा क्या, even though when we perform write operations on N1 or N2, these changes won't be propagated to N3 and N3 will have stale data, but it will be highly available. कि यूजर्स राइट भी कर पाएंगे और रीड भी कर पाएंगे. सीपी के केस में दे आर नॉट एबल टू राइट, so availability का issue है, but here they are able to write and read. Even though they will read stale data, but the data will be highly available. So this will be conserved in AP. And when there is network, then we can sync up all the data. So this is what CAP can do. System components. In this section, we will discuss the following core components and techniques used to build a key value store. First of all, we have data partition, data replication, consistency, inconsistency resolution, handling failures, system architecture diagram, write path, read path. Okay, so there are some basic core components and techniques. First is obviously data partition, and then we have data replication, then we have consistency, inconsistency resolution, handling features, inconsistent resolution, handling data partition, data replication, consistency, inconsistency resolution, handling features, and then we have system architecture design. Obviously, we have to design the system architecture, and after that we have read and write, read path and write path. Okay, so what is data partition? For large application, it is infeasible to fit the complete data set in a single server. The simplest way to accomplish this is to split the data into smaller partitions and store them in multiple servers. There are two challenges by partitioning the data. Distribute data across multiple servers evenly. Minimize data movement when nodes are added or removed. Consistent hashing can be used for this. Okay. So data partition is basically like, obviously we have used data, so we can't fit all the data into one server. So what data partition does is that it partitions the data and fits the data into multiple servers. So इसमें दो issue आ सकते हैं. First of all, the first issue is distributing the data evenly. कि हर server में evenly distribute हो data, किसी में बहुत ज़्यादा और किसी में बहुत कम ना हो. And the second issue जो आ सकता है, that will be minimizing the data movement when new servers or nodes are added or removed. तो we have seen कि अगर एक node remove या add हो जाए, तो minimize movement of data होना चाहिए. So इसका solution is basically consistent hashing, and we can also make virtual nodes in consistent hashing to make this even better. First, the servers are placed on a hash ring. In figure 6.4, 8 servers represented by S0 to S7 are placed on a hash ring. Next, the key is hashed on the same ring. It is stored on the first server and counted while moving in the clockwise direction. For instance, key 0 है, वो stored होगा S1 using this logic. Using consistent hashing to partition data has the following advantages. There will be automatic scaling. Servers could be added or removed automatically depending on the load. There will be heterogeneity. The number of virtual nodes for a server is proportional to server capacity. For example, servers with high capacity are assigned more virtual nodes. This consistent hashing obviously has two advantages. There is automatic scaling. Servers can be added and removed depending on the load, and heterogeneity. The number of virtual nodes in the servers will be directly proportional to server capacity. The second thing that we want to achieve in distributed key value store is data replication. To achieve high availability and reliability, data must be replicated asynchronously over n servers, where n is a configurable parameter. These n servers are chosen using the following logic. After the key is mapped to a position on the hash ring, walk clockwise from the position and choose the first n servers on the ring to store data copies. Okay. So for example, इसमें key 0 है, that will be mapped to S1, and let's just say n is equal to 3. So while moving clockwise from S1, we'll choose 3 सर्वर्स एंड उसमें हम सारा डेटा रिप्लिकेट कर देंगे. सो विल स्टार्ट मूविंग फ्रॉम S1, S2 and S3 एंड उनमें हम रेप्लिकेट कर देंगे डेटा. With virtual nodes, the first n nodes on the ring may be owned by fewer than n physical servers. Yes. To avoid this issue, we only choose unique servers by performing the clockwise walk logic. ठीक है. तो अगर virtual nodes होंगी, basically virtual nodes क्या होते हैं? We make for a node, we make some virtual nodes. जैसे S1 के लिए हमने S10 बना दिया. And we can also make S11, S13, and then we can have S2 or S2 के लिए virtual nodes, etc. So for example, इसमें जो है, if the key is stored here and we'll move, so उसका पहला जो server है, the data will be stored, obviously key will be stored in S1. So what we do in data replication is basically हम clockwise move करते हैं जिस server पर key store है, and for the next server, next n servers and n is chosen arbitrarily, we replicate the data onto them. For example, इसमें हमने movement शुरू करी, from S1 we'll go to S10, and obviously we will only use unique servers to prevent copying the same data into the same instances of the same server. We use unique servers. तो S10 में नहीं होगा क्योंकि ये virtual node है. S11 में भी नहीं होगा, S13 में भी नहीं होगा. It will store the data on S2 and it will store the data on S3. इन दोनों में it will store the data. So the data will be replicated on S2 and S3 and the data will be stored on S1, S2, S3. So we'll replicate it on the next three nodes. तो S4 में भी store होगा. So data is replicated on S2, S3, S4 and ऐसे कुछ होगा. इसमें हमारा n equals 4 है. If n was 3, कि हमें 3 सर्वर्स में डेटा रेप्लिकेट करना है, then it will be S1, S2 and S3. Nodes in the same data center often fail at a time due to power outages, network issue, natural disaster, etc. For better reliability, replicates are placed in distinct data centers and data centers are connected through high-speed networks. Okay. So एक ही data center में अगर हमने सारे replicate store करें and there is no issue, so the data can be fetched from any of the replicates. So what we do is we store the replicates at different centers and data centers are connected to high-speed networks. Third property is consistency. Consistency data is replicated on multiple nodes. It may be synchronized across replicas. Quorum consensus can guarantee consistency for both read and write operations. Let us establish a few definitions. N is the number of replicas. W is a write quorum of size W. For a write operation to be considered successful, write operation must be acknowledged from W replicas. Okay. A read quorum of size R. For a read operation to be considered successful, read operation must wait for responses from at least R replicas. ठीक है. So to maintain the consistency, we use quorum consensus. What quorum consensus basically does is for a write operation to be successful, the data, the write operation must be acknowledged from W replicas. And for a read operation to be successful, it must wait for responses from at least R replicas. For a write operation to be successful, quorum consensus states that the write operation must be approved from at least W replicas. It has to be acknowledged. And for a read operation to be successful, it must wait for responses from at least R replicas. Consider the following example shown here. Figure 6.6 with n equals 3. S1, S2, S2, and S0. So if we have a coordinator and it does an operation, put key 1, comma value 1. S1 will acknowledge it, S2 will acknowledge it, and S1 will acknowledge, S0 will acknowledge it. For W equals 1 does not mean data is written on the server. For instance, with the configuration of figure 6.6, data is replicated on S0 and S1 and S2. W equals 1 means a coordinator must receive at least one acknowledgement before the write operation is considered as successful. For instance, if we get an acknowledgement from S1, we can no longer need to wait for acknowledgement from S0 and S2. Coordinator acts as a proxy between the client and the node. The configuration of W, R, and N is a typical trade-off between latency and consistency. If W equals 1 and R equals 1, an operation is return quickly because the coordinator only needs to wait for a response from any of the replicas. If W or R is greater than 1, the system offers better consistency. However, the query will be slower because the coordinator must wait for response from the slowest replica. If W plus R is greater than N, strong consistency is guaranteed because there must be at least one overlapping node that has the latest data to ensure consistency. How to configure N, W, and R of data case? There are some possible setups. If R equals 1 and W equals N, then the system is optimized for fast read. If W equals 1 and R equals N, the system is optimized for fast write. If W plus R is greater than N, the strong consistency is guaranteed. Usually N equals 3 and W and R are equal to 2. And if W plus R is less than equal to N, strong consistency is not guaranteed. Depending on the requirement, we can tune the values of W, R, and N to achieve the desired level of consistency. So we have two values, W and R, and we can have different scenarios. For example, when W equals 1 and R equals N, then the system is optimized for fast write. When R equals 1 and W equals N, the system is optimized for fast read. When W plus R is greater than N, then high consistency is guaranteed because there will be at least one overlapping node that stores the latest data. And if W plus R equals N less than equals N, then strong consistency is not guaranteed. And depending on the requirement, we can tune the values of W, R, N. Consistency models. Consistency model is another important factor to consider when designing a key-value store. A consistency model defines the degree of data consistency, and a wide spectrum of possible consistency models exist. Strong consistency and a read operation returns a value corresponding to the result of the most updated write data happen. Client never sees out of date data. Weak consistency, subsequent read operation may not see the most updated value. Eventual consistency, there is a specific form of weak consistency. Given enough time, all the updates are propagated and all the replicas are consistent. Three types of consistency: strong, weak, and eventual. Strong may the client will always see the up-to-date data, the latest data will be seen. There will be non-consistency for all the users. On weak consistency may the client may not be able to see the most up-to-date data, it might see the stale data. Eventual consistency is that given enough eventual consistency is basically a form of weak consistency, but given enough time, all the changes will be propagated and all the replicas will be consistent to the most previous data. Strong consistency is usually achieved by forcing a replica not to accept new reads and writes until every replica has agreed on the current write. This approach is not ideal for highly available systems because it could block new operations. Dynamo and Cassandra adopt eventual consistency, which is our recommended consistency model for our key value store. From concurrent writes, eventual consistency allows inconsistent values to enter the system and force the client to read the values to reconcile. The next section is how reconciliation works with versioning. Inconsistency resolution versioning. Replication gives high availability but causes inconsistency among replicas. Versioning and vector locks are used to solve inconsistency problems. So obviously there will be inconsistency. Like replication gives us availability. Replication करने से availability आ जाती है, but it will also generate inconsistencies. So inconsistency resolution जो है can be done by vector locks or it can be achieved by versioning. So versioning means treating each data modification as a new immutable version of data. As shown in figure 617, both replica nodes N1 and N2 have the same value, which is John. Let us call the original value. Server 1 and server 2 get the same value for get name operation. Okay, next server 1 changes the name to John San Francisco and server 2 changes the name to John New York. So these two changes are performed simultaneously. Now we have conflicting values called the versions v1 and v2. In this example, the original value can be ignored because these modifications were based on it. However, there is no clear way to resolve the conflict between the last two versions. To solve the issue, we need a versioning system that can detect conflicts and reconcile conflicts. The vector clock is a common technique to solve this problem. Let us examine how vector clocks work. A vector clock is a server, version pair associated with a data item. It can be used to check if one version precedes, succeeds, or conflicts with others. Assume a vector clock is represented by D S1 V1 S2 V2 Sn Vn, where D is the data item, V1 is the version counter, and S1 is the server node. If data item D is written on the server SI, the system must perform one of the following tasks. Increment VI if SI, VI exists. Otherwise, create a new entry SI, 1. The above extract logics explain the example. One write handled by SX, then D1 will be SX, 1. Write handled by SX, then there will be a D2 which is SX, 2. Write handled by SY, then D3 would be SX, 2 and SY, 1. And write handled by SZ will be S D4 SX, 2 SZ, 1. And reconcile and written by Sx, then it will be Sx, 3 Sy, 1 and Sz, 1. A client writes data from D1 in the system and the write is handled by server X, which now has a vector clock D1 express, 1. And the client writes the latest data D1 and updates it to D2 and writes back on D1. So it overrides D1. Assume write is handled by the same server Sx, which now has a vector clock D2 Sx, 2. And the client reads the latest D2, updates it to D3, and writes it back. Assume the write is handled by server SY, which now has a vector clock D3, SX, 2 and SY, 1. Another client reads the latest D2, updates it to D4, and writes it back. Assume the write is handled by SZ, which now has D4, SX, 2 and SZ, 1. When another client reads D3 and D4, it discovers a conflict which is caused by the item D2 being modified by both SY and SZ. Conflict is resolved by client and updated data is sent to the soft. Assume the write is handled by SX, which now has D5 SX, 3 SY, 1 and SZ, 1. We will explain how to detect conflict shortly. Using vector clocks, it is easy to tell that version X is the ancestor, no conflict of version Y. If the version counters for each participant in the vector clock y is greater than or equal to the one in the version x. For example, the vector clock b is 0, 1 s1, 1 is an ancestor of b as 0, 1 s1, 2. There is no conflict, therefore no conflict is recorded. Similarly, you can tell that a version x is a sibling. A conflict exists of y if there is any participant in y's vector clock who has a counter that is less than its corresponding counter in x. For example, the following two vector clocks indicate that there is a conflict. D S0, 1, S1, 2, and D S0, 2 and S1, 1. Even though vector clocks can resolve conflicts, there are notable downsides. First, vector clocks add complexity to the client because it needs to implement conflict resolution logic. Secondly, the server version pairs in the vector clock could grow rapidly. To fix this problem, we set a threshold for the length, and if it exceeds the limit, the oldest pairs are removed. This can lead to inefficiency in reconciliation because the descendant relationship cannot be determined accurately. However, based on Dynamo paper, Amazon has not yet encountered this problem in production. Therefore, it is probable and acceptable solution for most companies. So basically, in consistency resolution and can we basically make vector clocks for each of the changes. And there are two things that we consider. Basically, ancestor relationship, ancestor relationship, and a sibling relationship. So for two vector clocks, they would be ancestor. A vector clock D1 will be ancestor of D2 if the version number in D1 is older than D2. For example, in D1 में हमारे पास था S0, 1 and S1, 2 and D2 में हमारे पास हो गया S0, 2 and S1, 2. Then obviously D1 is an ancestor of D2 and there will be no conflicts. For sibling, we have uh, two vector clocks and the version numbers in them are different, but they are not ancestors of each other. For example, one was S1, S0, 1, and we can have S1, 2, and similarly we could have S0, 2 and S1, 1. Means we- that is fully ancestor नहीं है एक दूसरे के, but they are siblings. And sibling wali relationship में there will be a conflict. In ancestor relationship does not have a conflict. Now, even though vector clocks can resolve conflicts, इसके भी downside है कि uh, first of all ज़्यादा कि obviously they will add complexity because the conflict resolution logic has to be implemented. And second was that the server from a virgin value वाला pair जो है it can increase. So इसका एक solution है that we can remove older server version pairs, but उससे क्या हो सकता है कि we might not be able to get the correct ancestor relationship. But as Amazon Dynamo के पेपर में लिखा गया है that they have not yet encountered this problem in production, therefore it is probable and acceptable solution for a company. Handling failures. As with any large system at scale, failures are not only inevitable but common. Handling failure scenarios is very important in this section. Include techniques to detect failures when we go over common failure resolution strategies. Failure detection. In a distributed system, it is inefficient to believe that a server is down because another server is. Usually, it requires at least two independent sources with information to mark a server down. As shown in figure 6.10, all-to-all multicasting is a straightforward solution. However, this is inefficient when many servers are in the system. All-to-all multicasting. So we have a many many-to-many relationship between servers. S0 can communicate with S1, S2, and S3, and similarly, S3 can communicate with all of them. S1 can communicate, and S2 can also communicate. This is known as multicasting. So this is one solution, but obviously this has a drawback. It is inefficient when there are many servers in the system. So better solution is to use a decentralized failure detection methods like gossip protocol. Gossip protocol works as following. Each node maintains a node member list which contains member IDs and a heartbeat counters. Each node periodically increments its heartbeat counter. Each node periodically sends heartbeat to a set of random nodes which in turn propagate to another set of nodes. Once the node receives heartbeats, membership list is updated to the latest one. If the heartbeat had not increased for more than predefined periods, the member is considered off. For example, for S0 membership list, um, it sends a heartbeat 102232 at time 12:1. It will send the heartbeat to S1 and S3 at times 224 and 237. Uh, in return, they will send a heartbeat to this. If the heartbeat is not increased for more than predefined period, the member is considered off. Node S0 maintains a node membership list as shown on the left side. Node S0 notices that S2 member ID heartbeat counter has not increased for a long time. Node S0 sends heartbeat that includes S2 info to a set of random nodes. Once other nodes confirm that S2 heartbeat counter has not been updated for a long time, node S2 is marked down and this information is propagated to other nodes. So this is the gossip protocol in which we send a heartbeat from each node, and this heartbeat is each node maintains a node membership list which contains a member ID and a heartbeat. Each node periodically increments its heartbeat counter. ठीक है सिर्फ एक एक नोड की जो हार्टबीट काउंटर है दैट रिमेन्स द सेम वो डिटेक्ट हो जाता है एंड देन दिस इंफॉर्मेशन इज प्रोपेगेटेड टू ऑल द नोड्स एंड वो भी चेक करते हैं एंड फिर इफ द नोटिस कि उसका हार्टबीट काउंटर नहीं बढ़ रहा है देन द सर्वर इज डिक्लेयर्ड डाउन हैंडलिंग टेम्पररी फेलियर्स If failures have been detected through Grover protocol, the system needs to deploy certain mechanisms to ensure availability. In the strict quorum approach, read and write operations should be blocked as illustrated in the quorum consensus section. A technique called sloppy quorum is used to improve availability. Instead of enforcing the quorum requirement, the system chooses the first W healthy servers for writes and the first R healthy servers for reads on a hash ring. Offline servers are ignored. If a server is unavailable due to network or server failures, another server will process request temporarily. When the down server is up, changes will be pushed back to achieve data consistency. This process is called hinted handoff. Since S2 is unavailable, figure 6 to 12, reads and writes will be handed by S3 temporarily. When S2 comes back online, S3 will hand the data back to S2, and this is known as hinted handoff. So in this case, S0, S1, and S2, S3, uh, S2 is down, so all the read and writes will be handled by this case में S3, and when the server is back, all the data will be pushed to S2. Handling permanent failures. Hinted handoff is used to handle temporary failures. So जो hinted handoff होता है, handoff है that is used to handle temporary failures. जितने भी temporary failures हैं, वो hinted handoff से handle हो जाएंगे. But this hinted handoff cannot implement floppy quorum, and this cannot be used for permanent failures, handling permanent failures. What if a replica is permanently unavailable? To handle such a situation, we implement an anti-entropy protocol to keep replicas in sync. Anti-entropy involves comparing each piece of data on replicas and updating each replica to the newest version. A Merkle tree, a Merkle tree is used for inconsistency detection and minimizing the amount of data transfer. Yeah. Listen, permanent inconsistency. If a server is completely gone permanently, then we have to use anti-entropy protocol. So anti-entropy protocol makes sure that data is consistent over all the servers, all the replicas for that matter. कि हर replica में same data है, and updating each replica to the newest version. So this updating can be done with the help of a tree, which is also known as a hash tree, which can handle the removal, can handle inconsistency detection and minimizing the amount of data transfer. It has to be a Merkle tree, a tree in which every non-leaf node is labeled with a hash of the labels or values in case of leaf of its child node. Hash tree allows efficient and secure verification of the contents of large data structures. Assuming key space is from 1 to 12, the following steps show how to build a Merkle tree. Highlighted boxes indicate inconsistency. Step 1. Divide key space into buckets. For an example, so a bucket is used as a root level node to maintain the limited depth for the tree. Once the buckets are created, so we create bucket for each server. Once the buckets are created, hash key in a bucket using hash each key in a bucket using a uniform hashing method. So हमने सारी keys को hash कर दिया, okay, and create a single hash node per bucket. तो हर bucket के लिए we have created a single hash node. हर key के लिए we have created a hash node and build the tree upwards till root by calculating hashes of the children. क्या हुआ server 1 में 5357 866 यहाँ ऐसे करते हैं कि new hashes will create. फर्स्ट ऑफ ऑल हर सर्वर को बकेट में बांटेंगे, हर सर्वर की रेप्लिका को बकेट में बांटेंगे. देन वी विल असाइन की वैल्यू पेयर with a good hashing method. हर की के लिए हैश कर देंगे एंड देन हर बकेट के लिए भी हैश कर देंगे एंड देन हर बकेट के हैश के लिए भी हैश कर देंगे एंड विल कंटिन्यू दिस. Compare two Merkle trees. Start by comparing the root hashes. If the root hashes match, both the servers have the same data. If root hashes disagree, then the left child hash are compared, followed by the right child hash. You can traverse the tree to find which buckets are not synchronized and synchronize those buckets only. Using Merkle trees, the amount of data need to be synchronized is proportional to the difference between two replicas and not the amount of data they contain. In real-world systems, the bucket size is quite big. For instance, a possible configuration is 1 million buckets per 1 billion keys, which only contains 1000 keys. Handling data center outage. Data center outage could happen due to power outage, network outage, natural disaster, etc. To build a system capable of handling data center outage, it is important to replicate data across multiple data centers. Even if a data center is completely online, users can still access data through the other data center. System architectural diagram. Now that we have discussed different technical considerations in designing a key value store, now we can shift our focus on architecture diagram. So we have a client which performs a read-write operation to the cord and the coordinator that handles everything. Main features of architecture are listed as follows. Client communicate with the key value store through a simple API, get key and put key, comma value. The coordinator is a node that acts as a proxy between the client and a key value store. Nodes are distributed or arranged using consistent hashing. The system is completely decentralized, so adding and moving nodes can be automatic. Data is replicated at multiple nodes. There is no single point of failure as every node has the same set of responsibilities. As the design is decentralized, each node performs many tasks as presented in the figure. So each node can perform a client API, failure detection, conflict resolution, failure repair mechanism, and replication storage engine, etc. Right now, figure 6.19 explains what happens after a write request is directed to a specific node. Please note the proposed design for read-write paths are primarily based on the architecture of Cassandra. Client. So a client sends a write request to a memory cache flushes it and also stable, and there is a commit log also. So we have two types of memories, a memory and this. The write request is persisted on a committed log file, okay, so that it can be rolled back, and data is saved in the memory cache, okay. When the memory cache is full or reaches the predefined threshold, the data is flushed to a SS table on disk. A sorted string table, SS table, is a sorted list of key value pairs. So basically, we have a write request, and the write request is logged, and write request is submitted into a log, and then the write request is stored in a memory cache. When the memory cache is full, the data is flushed onto the disk in a SSH table, which is a key value table of sorted key value pairs. Read path. After a read request is directed to a specific node, it first checks if the data is in memory cache. If the data is there, it returns to the client. If data is not in the memory, it will be retrieved from the disk instead. We need an efficient way to find out. SSH table contains the key. Bloom filter is commonly used to solve this problem. The read path is shown in the figure when data is not in memory. The system first checks if the data is in memory. If not, go to step 2. If data is not in memory, the system checks the Bloom filter. Bloom filter is used to figure out which SSH table might contain the key. SSH table returns the data of the data set. The result of the data is returned to the class. Summary. This chapter covers many concepts and techniques to leverage your memory. The following table summarizes features and corresponding techniques used for a distributed key value. Ability to store big data. Use consistent hashing to spread the load across servers. High availability reads. Data replication, multiple data center. High availability write, versioning, and conflict resolution with merge clocks. Dataset partition, consistent hashing. Increment scalability, consistent hashing. Heterogeneity, consistent hashing. Tunable consistency, quorum consensus. Handling temporary failures, sloppy quorum or and empty handoff. Handling permanent failures, Mercilessly, and handling data center audit, cross data center application. These are some reference materials. I will link. Yeah. So that is all for designing a key value store. We discovered a lot of stuff here. Like we discovered a single server key value store, and then we had a very detailed discussion on a distributed key value store. And we discovered a lot of topics, and there is also a summary here. I'll actually screenshot this something. Later. So yeah, this is a very good summary over here. And there are also some reference materials. So yeah, that's it for this chapter, which is chapter 6, designing a key value store. And we learned a lot of stuff here. What's are the concepts here? So I'll actually revise scoring bar, but I'll not make a video about it. So yes, that's it. Bye bye.